Alrighty, in this lesson we are looking at exponential and logarithmic equations. And I'm pretty excited about it because you're going to see a lot of problems that look really complicated, but we're going to break them down and learn some cool strategies for solving them. So let's get started. Our objectives, there's two: to apply the change of base formula to logarithmic expressions, and to solve really any kind of exponential or logarithmic equation that anyone could throw at us. That is our job in this lesson. So I want to begin with just some questions that you already know how to do. Here we are, we're given a logarithmic equation, and I'm asking for you to convert it to exponential form. So if you'll pause this video and try and work through that one. All right, you should have that base 3 to the 4th power gives you 81, and you could check that. Plugging in 3 to the 4th power in your calculator does give you 81. Let's try another one. Pause this video and convert that one to logarithmic form. All right, in logarithmic form, 2 is the base, and the exponent is the answer, so it's log of 256. Base 2 will give you that exponent of 8. All right, let's look at number 3. Here we're evaluating. Pause this one. It might take you a little bit longer to work through, but try that one out. The correct answer is 7. If you're not sure how to work through that one, take a look at the previous lesson for some of those properties. We have one more. Evaluate this one as well. Pause right now and work to find what that would be. All right, the correct answer is 2. If you all had questions on any one of these, just make a little note of that in your margin, and we can talk through them together when we're in class. So let's get started. I want to pose to you this problem. Solve 3, we're solving for x, the exponent. 3 to what power would give you 32? Take a moment to try and find that value of x. It's not 1. 3 squared is 9. 3 cubed is 27. And to the 4th power, that's not going to work either. So it seems that there is not an integer value of x that you could just plug in there and it'll give you 32. We're not going to have an integer. And so this is not something that we're able to just compute in our minds based on our understanding of exponents and how that works. Why don't we try another approach? Something we've seen before is, what about converting it to log form? Well, log form, usually we convert it to exponential form to try and solve that. And if you were to use your calculator, this is what you might want to start typing. You would use that log button, but your calculator, notice that there's no place to put your base. And so because there's no value there, it's that understood base 10, the common log, and we're not working with a base 10 here, we're working with a base 3. So don't worry, guys. We have a way to do this. We have a solution here. It is called the change of base formula. So what you can do with this change of base formula is, given that you're taking log of a with some base of b, if you want to find that value with the base, that common base, log base 10, you take log of a over log of b B is your base and it's in the bottom. That's how I'm able to remember that. You take log of the base in the bottom, log of that other value in the numerator. And let me work through an example here with you. Let's say we have the problem we were working with. 3 to the x equaling 32. Let's work through this. Converting to log form, like we did previously, log of 32 base 3 is going to give us that x value. And now we can apply the change of base formula. So that's going to be log 32 over log 3. That's going to give you x. Make sure you're taking log of 32 over log of 3. You're not going to be dividing 32 by 3. It's log of 32 divided by log of your base going in the bottom, which is 3. And then you use a calculator. It would look like this. You would take log 32, make sure you close up that parenthesis, and then divide it by log of 3, and that will give you 3.1546. That's to the nearest 10,000th. You would just want to check whatever problem you were working on. They'd probably tell you what to round to. So there you have it. That is the change of base formula in action. Let's look at this example here. It's in exponential form, so let's try, because we have kind of like a interesting exponent there, it's x plus 5. Watch what happens when we take the common log of each side. Log of 4 to the x plus 5 equals log of 12. Now, because it's in that log form, remember when you're raising something to a power, that power property for logarithms, that x plus 5, actually is the p-value that you're going to multiply your log 4 by. Okay, so now it's not in the exponent. This is very nice. We can solve for x now by dividing each side by log of 4. And then you would just subtract 5, and that's how you'd get x isolated. I would use my calculator here, and first I would divide log 12 by log 4, and then I would take that answer and subtract 5 from it. So it is approximately negative 3.2075, and that is your answer to the nearest 10,000th. So there you have it. That's kind of the approach you'd want to take if you had a binomial like that as your exponent and you were trying to solve. A little different example here. We're solving for x, and x is the number that you would get if you raised 27 to 2/3. You would convert this to log form, exponential form, to see that. 27 to 2/3 would give you x if you did that log loop trick. You guys know that one. And so pretty straightforward here. You can just use your calculator, take 27, raise it to the 2/3, make sure that that is in parentheses, otherwise your calculator might not interpret that correctly, and it is 9. Here's another example, kind of along the same path. Log of 6 base 9, log of x base 9 gives you 3/2. Because you have two logs with the same base and they're being added, you can apply that product property and kind of condense that. So it's log of 6x, we're multiplying there, base 9 will give you 3/2. Now that it is just one logarithm, we can use that loop trick to write it in exponential form. That's 9 to the 3/2 equals 6x. I'm getting a little ahead of myself here because I know that 9 to the 3/2 is 27, and that is equal to 6x. isolating, you would be dividing 27 by 6, and you can simplify that, and it is 9/2. So there you go. That is our second part of that third example. And I have just one more here for you. We have log of x equals 5.37. And we're trying to figure out what is x. You might be right now a little stumped. What do I do? You can't just type that into your calculator. We would want to convert this to exponential form. And this is where you have to recall, if you don't see the base, you know that it is an understood 10. So that is 10 to the 5.37. It will give you x. And use your calculator. That is a perfect time to pull it out and check. 10 to the 5.37. I'm just going to round that to the nearest whole number. That is approximately 234,423. Pretty large. That's what happens with exponential functions. You don't have to increase very much for things to get tremendously large. So ladies and gentlemen, that is all. Those are just some examples. I'm kind of whetting your appetite. This is like an appetizer to kind of get your gears moving, and you're seeing how you can use these properties, how you can convert to solve these exponential and logarithmic equations. So that's all I have for you guys. See you later.